Hi everyone, my name is Gillian, and today I'm going to be talking to you about SCAMPP+FastTree, which is a method we came up with to improve scalability for likelihood-based phylogenetic placement. This work is in conjunction with Professor Tandy Warnow, who's a professor at the University of Illinois at Urbana-Champaign. So to start off with, I want to explain what phylogenetic placement is. Phylogenetic placement is the process of placing what we call query sequences into backbone trees. We start off with a phylogeny or an evolutionary tree, which is built on usually a set of aligned sequences. So here I have an example of S1 through S4. These are my aligned backbone sequences, which compose this backbone tree topology that I have on the S1 through S4 sequences. And I also have this query sequence Q1, which you can notice is not aligned to our existing backbone sequences. The output to a phylogenetic placement method would be something like Q1 here on the right-hand side, where Q1 has been placed into our existing backbone topology. And so a phylogenetic placement method is challenging to come up with because phylogenetic placement becomes challenging when we have large numbers of sequences in our backbone. However, you can imagine that it's useful to update large trees, especially when you don't want to recompute the entire tree, which is a very costly and computationally expensive maneuver. The leading phylogenetic placement method right now is p-placer, which is a maximum likelihood method, but unfortunately p-placer fails in backbone trees of larger than 5,000 sequences. What we're presenting here today is p-placer's SCAMPP+FastTree, which capitalizes on two main developments. The first is that we want to replace the numeric parameter estimation software RAXML with FastTree. And the second is that we want to use SCAMPP, which is a divide and conquer framework that selects a placement tree for each query sequence. So we place the query sequence into this placement tree. This placement tree is smaller than the full backbone tree. And so by placing it into a smaller backbone tree, we can use that placement to resolve a placement into the full original tree. So using these two techniques together, p-placer's SCAMPP+FastTree improves the scalability and accuracy compared to existing phylogenetic placement methods. We've tested on a multitude of data sets, both simulated and biological, at several different fragmentary query lengths. And we do this because queries can be queries which are extremely fragmentary, say 10%, are much harder to place than if we have less missing data, say full length query sequences. So here I'd like to go over some main takeaways from our results. The first is that p-placer-FastTree, which is our new proposition where we only replace RAXML with FastTree. p-placer-FastTree runs on large data sets where p-placer-RAXML does not, but it doesn't compromise on accuracy when they both run. So here you can see I'm presenting on 3 different data sets, all in full-length query sequences, and in yellow we have p-placer-FastTree, in blue we have p-placer-RAXML, in the top row we have delta error, and in the second row we have average time. And so our main takeaway here is that p-placer-FastTree is able to run when p-placer-RAXML is not. This dataset has 78,000 sequences, and so you can see that even at 78,000 sequences, the p-placer-FastTree is able to run, whereas p-placer-RAXML fails due to this lack of scalability. When they are both able to run, these are in 2 different model conditions, but also simulated data. When they're both able to run, we can notice that there actually isn't that much of a difference between runtime in terms of runtime or delta error between these 2 methods. So this means that using p-placer-FastTree doesn't seem to compromise on accuracy. Our second takeaway here is that p-placer-FastTree produces the best delta error accuracy, but is extremely time consuming. So in this plot, we're exploring a different data set. This is RNA-Sim50K, which contains 50,000 sequences. This is RNA-Sim200K, which contains 200,000 sequences. And in blue, again, we have p-placer-FastTree. And now we've introduced our p-placer-SCAMPP+FastTree. We have several different variants of p-placer-SCAMPP+FastTree because we can place into placement trees of different size. So here we're setting that to be 10,000, 20,000, and 40,000. And what we'd like to observe here is that on all 3 data sets, p-placer-FastTree and the p-placer-SCAMPP+FastTree variants don't seem to be too different in terms of accuracy. You see here that on RNA-Sim50K, when we're placing full-length query sequences, the accuracy is all very similar, same on RNA-Sim50K with 25% length. And then on RNA-Sim200K, which contains 200,000 sequences, p-placer-FastTree is unable to run. So although p-placer-FastTree was more scalable than p-placer-RAXML in this first takeaway, we can find that p-placer-SCAMPP+FastTree is actually more scalable. It's also interesting to note that on a by placing into a subtree of only size 10,000, we can achieve similar accuracy to when we place into the full subtree size. This gives us an advantage because although accuracy is about the same, we actually gain some advantage in terms of runtime, although slight here. We do see a significant advantage in terms of scalability in this third data set containing 200,000 sequences. If we move on to the NT78 dataset, we show a second plot here, and we can notice that the difference between the three columns is the length of our query sequence. So in particular here, we see that on the shortest query length with the highest missing data, we see that SCAMPP+FastTree is actually incurring quite a lot of delta error, but it decreases as we increase our placement subtree size. Unfortunately, we also see that the placement subtree size increases our runtime slightly and our peak memory. Here we have a runtime accuracy trade-off. Finally, I explore these same trends on the biological data sets, and we notice that we have the same, approximately the same trends on biological data as well. So again, our main takeaways are that FastTree is more scalable than XML, and that SCAMPP+FastTree is more accurate than comparably scalable methods. Thank you for listening.